Now that we know what overfitting is, how can we avoid it? When we're using linear and logistic regression models, we can only add variables that make a substantial improvement in the explanatory power if we want to avoid overfitting. So if we were to look at the R-squared, for example, in a linear regression model, we want to see the R-squared go up substantially when we include a new variable. If it only goes up by a tiny decimal, it's not really adding much to the model, and this is an identifying factor. So we can use variable selection to eliminate things like that, to eliminate the unnecessary variables we may have added inadvertently. There are 5 variable selection methods, and we're going to breeze through 4 of them and focus on the last one, which is my favorite. The first method is hierarchical selection. And you know what the word hierarchy means. So this follows along with that. We add the variables first that we know are going to be useful in the model. Maybe this information comes from previous research, from our intuition, or from our expectations as researchers. And after that, we add variables one at a time, choosing the best first, and maybe that comes from our correlation metrics or intuition about which one's going to be best. And we add those one at a time, and each time we make an addition, we look at that R-squared or the prediction accuracy or some other measure of fit to see that we've really improved the model. Another variable selection technique is called forced entry, and it's not really a variable selection technique, it's more of a policy. This is when someone creates a model on their best guess and they put in all the variables at the same time. You're not adding them one at a time. You run the model one time and take the results as the truth. There's no adding and subtracting to see what works best. Completely the opposite of that method is called all subsets selection. And what happens here is that you run the model for every subset of variables. So if you have 3 variables as your potential X variables, your predictors, you would try it with variable 1, then with variable 2, then with variable 3. Then you'd try it with variable 1 and 2, 1 and 3, 2 and 3, and then a model with all 3 of them. So you're trying every possible combination of variables. And then you just choose the model that has the highest R-squared or the best prediction accuracy. But the problem I see with this is that you're running through every possible combination and you're really exhausting the potential, because we've said that the more tests we do, the more t-tests we do, the more hypothesis tests we run, the more likely we are to find a mistake. So we do want to balance the number of tests with that last method of forced entry. It seems a little silly to just run it one time without considering, the potential for change and how it could improve the model. But it also seems silly to run them all and choose the best one, because it's possible that the best one just looks the best by chance. So I think there's a happy medium that we can find. Forward stepwise regression is a common technique where we start with no variables and we choose at each step the next best addition. So if we start with nothing, we choose maybe from 3 variables which one is going to improve our R-squared the most at this first round. And once we decide that, we add it to the model. Then on round 2, we'll choose from the remaining and see which one will add to the R-squared the most. And then we just stop when there's no major improvements that come from adding a variable. So if we add 4 variables and then any remaining variables only add about 0.5% to the R-squared, we can finally stop adding to the model because we've exhausted our improvements. Finally, backward stepwise selection is the technique that I and a lot of researchers think is the most appropriate. In this situation, you start with all the variables in the model and you slowly remove one variable at a time, whichever variable is contributing the least. And you stop whenever you've removed all of the variables that really aren't contributing anything. You wouldn't want to remove any variables that seem to contribute a lot to the explanatory power or the prediction accuracy of the model. Now, some researchers take issue with stepwise selection. They think this method relies too much on the model fit, and I don't disagree with that. The R-squared tells us how well a model fits the sample data, not how well it solves the problem. We're looking for a generalized understanding of what's going on within a population, but the R-squared is just saying, hey, you're doing a great job here with this sample. And since we're going to look to the R-squared increases and decreases, or maybe we're doing a logistic regression model and we're looking at the AIC, or maybe we're looking at prediction accuracy, but we're looking specifically at what's happening in this sample. We're not making a judgment based on how well it fits other data. But I think that's where our tests of both the training performance and the test set performance in terms of prediction accuracy, that's where that comes in. If we make our judgments based on model fit, and then we test our findings in that test set that we've preserved, then we can really be sure that we're on the right track. Generally, researchers prefer backward stepwise selection for variable selection purposes. And the reason is because some effects exist only when variables are together in a model. So multicollinearity does have an effect. When two variables share a relationship and they sort of contribute to one another's explanatory power, that's something we want to recognize. And if we use forward stepwise selection, where we select a variable one at a time, then we're not allowing for those forces to have their effect. So backward stepwise selection allows those things and only removes one thing at a time, being careful to allow the effects of all the other variables to exist together while we choose the best model. So we're going to use backward stepwise selection in this class.